Of all the metals, the nickel value chain is one of the most complex. On a volume basis, it sits somewhere between a major metal value chain like copper and a minor metal like cobalt. It's not quite an ancient metal like copper or gold, and not quite a modern metal like uranium or aluminium. There are many product forms. At the system level, these form an interconnected web of substitutes or partial substitutes nested within certain technical and economic constraints. On the demand side, nickel can be found in a bewildering array of metallurgical and chemical applications. Nickel is an alloy that increases strength, toughness, and corrosion resistance. First uses are grouped into stainless steel, alloys, plating, and batteries. Nickel touches almost everything in our material world, from screws, nuts, bolts, brackets, plumbing, sinks, washing machines, refrigerators, handrails, guitar strings, medical instruments, and cutlery. If nickel was not used directly in a finished good, it's probably part of the housing or frame, and it was all machined with tools containing nickel. It's also a key part of the cathode in certain types of lithium-ion battery found in consumer electronics and electric vehicles. Nickel processing is heavily influenced by geology. There are three main types of ore that you need to know about. Sulfides. Commercially viable deposits are mostly found in temperate climates like Canada, Russia, and Australia. Saprolite and limonite. These are subtypes of laterites and are mostly found in tropical climates like Indonesia, Philippines, New Caledonia, and Brazil. Before the scale-up of nickel mining in Indonesia from 2006-2007, sulfide deposits were the backbone of the industry. These deposits can be highly valuable, but they are also geologically messy. As you can see from the diagram in the bottom left-hand corner, mineralization occurs in multiple different ways, making these deposits unpredictable and difficult to mine. On the processing side, the basic flow sheet for sulfide ore is similar to other base metals such as copper, lead, and zinc. Following crushing, grinding, and flotation, a concentrate is produced which is smelted into matte. This sulfide matte is then refined into nickel of 99.8% purity or above in the form of cathodes, briquettes, pellets, powder, and ingots. A key difference with other base metals is the significant variation in refinery processes. Each sulfide refinery has a unique flow sheet and consequently very high levels of vertical integration. Laterite deposits are soft, close to the surface, and run in relatively continuous layers. Mining is more like earthworks than hard rock mining. A key step in the mining process is stockpile management to separate saprolite, limonite, and waste, as well as blending to control for grade, iron, magnesium, and silica. The high-grade saprolite is dried and placed in a rotary kiln, followed by an electric furnace, or RKEF, to make into a nickel pig iron. NPI can be used directly in stainless steel or converted into matte. Matte can be refined into nickel metal and nickel sulfate via metal or even directly by acid leaching. Limonite ore undergoes a hydrometallurgical process called high-pressure acid leach, or HPAL. The key step is high-pressure leaching at around 40 atmospheres in a special tank called an autoclave. This is followed by other processes like neutralization, washing, purification, solid-liquid separation, and precipitation. In the noughties, there was a new wave of HPAL projects, and many suffered serious technical issues, mostly relating to the performance of equipment at high pressure. and subsequent capex blowouts. In 2012, Ramu River was developed in Papua New Guinea. This success formed the blueprint for the Indonesian H-Powers built from 2021, including at Obi Island, Weda Bay, and EMIP. This diagram merges the sulfide and laterite flow diagrams and strips away the processes so we can just focus on the interconnection between different nickel products. LME deliverable nickel is more than 99.8% pure in the form of cathodes, pellets, briquettes, and rounds. The LME price has been the anchor point for the nickel industry since the 1970s. Intermediate products are often sold relative to this benchmark using a payable. For example, NPI may be sold on an 80% payable to the LME, which is an 80% of the nickel metal price multiplied by the amount of nickel contained. Nickel sulfate is often reported as a premium or a discount to the metal price. Whilst the nickel metal price is still the most liquid, two developments over the past 20 years have diluted its dominance. First, in the late 2000s and 2010s, there was a massive scale-up of the volumes of NPI, which is used directly in stainless steel making, mostly in Asia. This is partly to deal with ongoing growth in stainless demand, but also so nickel metal units could be diverted to rapid growth in demand for nickel sulfate. This has led to an independent price indices for NPI. A recent wave of new H-Powers has led to meaningful volumes of MHP, as well as independent reporting of nickel sulfate prices. A distinction between Class 1 and Class 2 emerged in the late 2010s and early 2020s, reflecting the relative surplus of nickel units available for stainless and the shortage for batteries. Large structural price dislocations between Class 1 and Class 2 disappeared by the mid-2020s for a few reasons. Ramp-up of MHP production. MHP can be directly refined into nickel sulfate, making it the cheapest route to sulfate, thus eliminating the inefficiency of making large volumes of sulfate by dissolving metal in acid. Another capacity bottleneck that limited interchangeability of nickel units was matte and refining capacity. NPI scale-up in China and Indonesia initially occurred without matte converters and refineries. This has since been resolved, and producers now have optionality to shift nickel units between Class 2 and Class 1 markets when price spreads widen. Today, many in the media and climate ecosystem often talk about H-Powers and MHP as being for batteries. Whilst this is true to a certain degree, the reality is the cost differential between converting MHP to metal versus sulfate is only about $500. Sustained discounts on sulfate to the metal price will encourage producers with refining capacity to shift MHP flows from nickel sulfate to metal. In short, outside short-term dislocations, this complex system is highly flexible. Geology is the primary factor for choice of smelting and leach technology. After this stage, processing is orientated towards matching nickel units to the form required by the first user. Supply and demand of different intermediate products is reflected in the dynamic system of price spreads that creates signals for matte converters, refineries, and stainless mills to direct the flow of their marginal nickel units. 66% of nickel demand is from stainless. Global stainless demand has a steady growth profile averaging 3-4% a year, correlates well with economic growth, albeit a little bit more cyclical. Nickel in alloys and plating has a variety of uses and drivers, from more mundane equipment to high-end applications in aerospace and defense. Despite being just 18% of demand, batteries get a disproportionate amount of attention for two reasons. Rapid growth in demand from EVs for lithium-ion batteries, mostly in the 2010s, push by companies and governments to associate mining with green products and the energy transition. In the 2010s, NMC batteries, that is, batteries with nickel, manganese, cobalt cathodes, were strongly driven by performance and range. In recent years, the outlook for NMC market share has declined significantly. LFP, lithium iron phosphate batteries, are rapidly becoming the standard for EVs and have more than 90% of the market for ESS, energy storage systems. When selecting a battery, you're thinking about the trade-offs between cost, performance, and safety vis-a-vis the end use. In the case of an EV, LFP will be cheaper to produce because iron and phosphate are much cheaper than nickel and cobalt. However, the full cost is more than that. For example, NMC batteries require more complex cooling systems to LFPs for a comparable amount of safety. So the total cost of deploying it in a vehicle is even higher. Geographic concentration of nickel and copper supply means lower security of supply and higher price variance compared to iron and phosphate. Given the high overheads in battery and vehicle production, there is a strong incentive to value the more risk-averse option. LFPs are generally safer, and the performance gap has been closed, leaving few use cases where NMC is a serious advantage. Aside from Tesla, Chinese companies now dominate the EV market, producing vehicles that are cheaper and more advanced than the legacy automakers by leveraging a deep industrial base, thick labor pools built around batteries and manufacturing, and access to natural resources. Whilst NMC batteries will continue to be an important part of nickel demand, growth is unlikely to match the double-digit CAGRs we saw in the 2010s. The modern state of the nickel market cannot be explained without telling the story of Indonesia. Pre-2006-2007, nickel supply mostly came from sulfides and was controlled by large Western companies, plus Japan. Following a price spike, China started scaling up a new business model based on MPI capacity and imported ore from Indonesia and the Philippines. In 2009, Indonesia replaced contracts of work with a mining business license system which separated exploration and exploitation, mandated that IUPs must process their ore domestically, and mandated foreign investor divestment. Implementation was messy, and all bans and relaxations occurred against the backdrop of a volatile current account and fragile investor confidence. Given the flare-up in demand from batteries and the concentration of untapped nickel resources in Indonesia, access to these resources became a leverage point, and China has now invested more than $50 billion in Indonesia to develop RKEFs, H-Powers, MAC converters, refineries, as well as the world's largest stainless steel mill. And that's together with all the supporting infrastructure like roads, ports, and power plants. By some measures, the supply concentration of the nickel market in 2026 is close to 70%. Costs of nickel projects outside the combination of Indonesian geology and Chinese engineering are prohibitively expensive, leaving little room for new entrants. At all-in costs of $10,000 to $11,000 per ton of nickel, Indonesian H-Power projects will continue to be built, although perhaps less rapidly than before given higher environmental scrutiny and slowing demand. The key driver of nickel prices is now the tension between policy decisions in Jakarta, which are largely aimed at constraining supply through RCABs and other measures, and policy pressure from China, largely targeted at maximizing allocations and approving new projects.
When the market moves, I know the signs, nickel dreams and copper lines, spotlight shining on the ore, steel's got rhythm, I want more. Hey,